The architectures to trade off performance versus debug for software development on emulation platform. Abstract. In pursuit of facilitating early software development, it's always been necessary to speed up simulation and emulation platform. Currently, emulation platforms can reach peak performance of several megahertz. However, when a debug is required, the speed drops to 10 to 100 kHz. In this paper, we propose switchable architectures to enable performance and debug ends of the software development spectrum. Introduction. Development of the software is an essential ingredient of any SoC project. This software effort is required for many reasons. Some of them include developing a boot code for SoC, establish the critical security parameters of the SoC, and low-level drivers for each of the preferred components and software applications that interact with the hardware. For example, a video processing software running on SoC may require interacting with a video processing hardware unit. In the past, software development for SoC would begin after the chip has been fabricated. As the silicon can run at gigahertz speed, with current time to market consideration with this approach does not work, as it may take several months or even years to complete the software development. In addition, any hardware change is extremely costly at this stage. Hence, it's essential to start software development early in the SoC development cycle. Early software development ensures that hardware and software work seamlessly with each other. Any RTL both exposed during software development can be easily fixed by changing the RTL. So using this shift-left strategy results in a software being ready and available when the chip sample comes back from the fab. But there is one main question that needs to be answered. What is the right platform to use for such early software development? There are several possibilities, each with of which own pros and cons. This include a. Simulation platform. As the RTL, test bench, and tests are already running on a simulator, it appears to be an easy way to use the platform for software development. One can load the entire software stack in RAM using ReadMH and start the simulation. This platform is cycles accurate and offers full visibility to each signal. Complete debug of both hardware and software is feasible. However, the main drawback is the performance. Software teams are not gonna be excited compiling or running their software on a platform runs at a kilohertz speed. Instruction set simulators. This is typically a simulation model of processor. For example, Spike is a RISC-V functional ISA simulator. It models the instruction set architecture of RISC-V core and cache system. The ISS model mimics the behavior of the processor by reading object code and from file and maintaining the values of internal registers. The ISS models are instruction accurate but not cycle accurate. They output a trace of all instruction as it is being executed. The performance of this platform is very high as we are executing a fast motor of processor, but it does not have any knowledge of the rest of the SoC. C. Virtual prototype platform. With these platforms, one can model the entire SoC, including all the preferred components. Software development can start on this model even before the RTL is complete. These models trade off the cycle accuracy for higher level performance. Although the software developers have a high performance platform, developing and maintaining this platform is labor intensive. Moreover, the bugs in the RTL may not be exposed by this platform as the RTL is not used in these models. Emulation platforms. These platforms allow the user to synthesize the DUT and map them into internal hardware components, for example, VGA or special purpose processors that reside on the emulation board. The test bench is typically not synthesizable and runs in a simulator on a Linux workstation, sometimes referred to as a modeling host. The performance of the emulation platforms, which can be 1,000 times better than a simulated performance, depends on the interaction between the test bench running on a Linux workstation and the DUT running on the emulator. The lesser the interaction, the higher performance gain. This is shown in the following figure. In signal-based acceleration, the interaction between DUT and test bench is pure signal-based, and each signal transition is communicated within the two domains. Performance gain is limited by the constant synchronization required between the simulator and emulator. In transaction-based acceleration, the communication between the test bench and the DUT is based on the transactions, which are typically larger chunks of data. This method further improves the emulation performance as the frequency of the syncs between the test bench and the emulator decreases, as compared to signal-based acceleration. In circuit emulation mode provided the highest performance on the emulator because the entire test bench and DUT are running on the emulator to monitor the signal activities from DUT. Hardware prefers, for example, speed bridge, are sometimes attached to the emulator. Hybrid emulation platform here. The RTL of the CPU is placed by C-based model, the ARM fast models, but the rest of SoC is synthesized onto the emulator. This approach improves the boot performance. Debuggability of the SoC is still good because the rest of RTL is synthesized on the emulator. Due to the interaction required between hardware and the software, that is the fast model of the processor, the performance will not equal to the ICE mode performance. When using the emulation platform, we use the RTL mostly as is. There is no need to develop separate model of the hardware for the purpose of verification of the software development. The original RTL is directly synthesized onto the emulator. Any potential bugs in the original RTL will be exposed during emulation. However, the interaction and sync with the simulator and emulator has a significant impact on the overall performance. Our goal was to come up with a solution that can be obtained the best possible performance on the emulator, while retaining the ability to run debug when necessary. Chapter 2. Performance and debuggability requirements. As shown above, the verification performance varies of several order of the magnitude depending on the architecture chosen for emulation. Higher verification performance, such as ICE mode, also implies lower debuggability. While ICE mode is useful for software development, the lack of the debuggability impedes the chances of debugging the software running on a processor. Also, a pure ICE mode requires speed bridge adapter for prefers, restricting the scope of the usage. So, an essential requirement for debugging SoC running on the emulator is that a DUT running on the emulator and the rest of the test bench running on the simulator be driven in a lockstep fashion synchronously by a single clock. Effective debugging also requires the use of certain components such as a tracer a component that prints out the detail of each required instruction, and B, debugger, a component that enables us to set breakpoints on the software and examine the values. The tracer debugger must be in sync in the rest of the RTL running on the emulator. On the other hand, an essential requirement for high performance is that a DUT running on the emulator executes independently of the test bench running on the simulator and synchronizes as infrequently as possible. Such a synchronization method will ensure that the hardware can perform the maximum allowable speed without stopping and syncing with the simulator. Components such as the tracer and debugger are not required when running the SoC in high performance mode. It is also essential that the solution is designed to easily switchable between a performance mode and a debug mode. The test bench architecture and the test needs to easily switchable between performance mode and debug mode of the emulator. Chapter 3. Our solution. We propose a switchable architecture solution to manage the contradiction requirement of the debugging and performance. The proposed architectures are A. Debugger-focused architecture and B. Performance-focused architecture. So we realized that the building and maintaining two separate architecture for emulation would be an expensive proposition. Hence, we designed the architecture to share the much code as possible, so we ensure that the RTL used in both architectures are same. This provides the following benefits. A. A bug discovered in the RTL in one mode is easily reproducible with the other mode. B. Synthesis effort to share the code both modes as the DUT is the same. However, in performance-focused architecture, there are some additional components instantiated in the emulator. Our solution also uses virtual prefers. We built virtual prefers for GPIO, UART, and the other required external interfaces. These virtual prefers receive the data from the SoC using the communication channel between the emulator and simulator. The received data is proposed either printed out on the terminal or stored in a file. This makes it easy to understand the cause of the failures. The use virtual prefers impact the performance, but it enables broader usage of the emulator. Although our solution is generic and can be implemented in any of the commercial emulator, we have used the Palladium emulator to implement our solution. This implies some of the internal features offered by the Palladium has been used in our implementation. For examples, the IX clock gen has been used to generate clock generator component to the emulator. Debug-focused architecture, DFA. The debug-focused architecture is shown in the figure below that contains three parts. 1. The main SoC is synthesizable and runs on the emulation hardware. A simulator running on the Linux server contains the following. A. Virtual prefer component. B. Debugger interface component that interfaces GPD. C. Processor, Ibex, tracer component uses the RFFA I interface on Ibex. Signals are transferred to a simulator using signal-based acceleration. The tracer receives the required instruction and prints them to the tracer log file. Clock and listen generator are included in the simulator side and the values are synchronized with the Palladium hardware. C. Simulation control engine serves the following purpose. Load up the code, forcing of the signal if needed, and of test detection mechanism to detect the test completion and exist in the emulation engine. DBA implementation is characterized by the following. A. Software debugger interface to debug the binary code executing the SoC, such as the debug interfaces will enable software developers to set breakpoints and examine the values of the value of random registers. B. Instruction tracer to trace every instruction being retired on the CPU. The tracer capability will give real-time pictures of instructions as they are fetched and processed. C. Model all the prefers that can process all the signals sent out of the SoC. For example, the output from the UART port is decoded by a prefer, real or virtual, and transfer the data to an output device. D. Waveform dumps may be necessary for post-simulation debugging activities using tools like SimVision. Emulators typically have powerful features for managing and viewing the waveforms. Performance-focused architecture (PFA). The performance-focused architecture contains three parts. 1. Synthesized design running on the emulator include A. The main design SoC. B. Clock and reset generation circuitry for the SoC. The native clock generation capabilities of the emulation performance are used to specify the clock features. A core QEL file is used to specify the clock as preference, and in the internal tool is used to generate the clock component. The generated clock component uses a native Cake API. C. Transaction buffer. To keep the emulator and simulator running asynchronously, it's necessary to capture all the output from the I/O component of the SoC. In this case, we have built the transaction buffer that captures all the output of the UART and GPIO. This transaction buffer is retrieved periodically by the simulator and data stored in the logs. 2. Test bench running on the simulator only contains the virtual GPIO and the virtual UART component. Here, these components are driven by the independent clock is not synchronized with the emulation clock. 3. The simulation control engine that serves the following purpose: load the boot code, forcing the signals if needed, and at the end of the test detection mechanism detect the test completion and existing the emulation engine. In summary of the main differences between these architectures are highlighted below. DPA, debug-focused implementation, as performance-focused implementation. Result: we developed a PFA and DFA for a RISC-V based SoC platforms. Internal codename Athos based on the Ibex core. This internal SoC was designed in System Verilog with an open source low risk component, so that the SoC contained two buses, a main bus and a preferred bus. These interconnected structures are based on the tie-link protocol, so that the SoC are also contained a couple of prefers UART, GPU, GPIO, and communicate with the external world. The entire SoC is designed for expandability. We are using these SoC as the base case building for other projects. The software test stack for a SoC contains many layers, including a hardware abstraction layer, runtime library, and boot code for SoC, the harness, and the user code application. Software running on the CPU controls the initialization, reading, and writing of the values on these prefers. Only by layers of software are written in C, and our goal was to run all software both modes. We implemented a PFA and DFA architectures for the Athos SoC on the Palladium 6 emulator. The implementation highlights: we connected the tracer through the RFVI interface available in the Ibex for the DFA. DFA was debugged enabled throughout the OpenOCD interface. Prefers were on borders as virtual I/O blocks. The compilation of both hardware and software was done with the ProtoForge, and proprietary build engine that managed both hardware and software builds. RISC-V toolchain was used to compile the boot code, and the library and tests run tests run on the SoC. We compiled CoreMark benchmark test cases for a RISC-V processor and ran it on both DFA and PFA. Using Palladium, we measured the number of TB stings for the test benchmark. As expected, the number of the TB stings was 300% higher for DFA. So the results show close to a 100 times difference in the performance between the DFA and the PFA for the CoreMark test case. The emulator usage percentage increases significantly in PFA modes as the emulator is running with its own clock and minimizing the sync with the test bench. These architectures can switch to easily depending on the use. For nightly regulation, the DFA mode would be ideal, while for debugging failure, DFA mode would be ideal. References. Okay, today I read this paper, Architectures to Trade-off the Performance versus Debug for Software Development on Emulation Platform from DevCon Japan 2024. Thank you for your time. See you next time.